Today I'm going to talk about our integrated design project. We are from group 8. Before I go to present, I'm going to introduce my fellow friends here. First, me Sharon. Second is Mohammad Arizan. Third is Ainun Jareha. Third is Deborah. So we are from group 8. Second, in our integrated project, there are two parts. First is thermodynamic part, second is separation part. In chapter 1, I'm going to talk about the introduction. Now I'm going to talk about the physical property of methanol. First is it's highly toxicated, second is flammable, colorless and volatile, third is exit as a polar liquid at standard room temperature, fourth is boiling point is at 64.7 degrees Celsius, fifth is melting point and freezing point at 93.9 degrees Celsius. In here, we are going to talk about the usage of methanol. First, perfect replacement for conventional fuel. Second is widely used as a solvent. Third is serve as a building block to produce other chemicals such as formalin. Fourth is produce acetate acid through the cavity process. I'm going to talk about the plant capacity. So in our integrated project, we apply steam methane reforming MSR technology. Next, I'm going to talk about the selection of instrument. Okay, these are the parts we are used in our integrated project. First, the reforming reactor, condenser, compressor, methanol reactor, cooler, syngas recovery unit, three-way valve, pump, methanol purification unit with reboiler and condenser. So next, my friend Ainun will continue. Thank you.
Thank you, Sharon. And I am Ainun, and I will be presenting chapter 2, which is about process flow diagram. Firstly, need to consider the overall material balance of the system so that our system will follow the law of conservation of mass. This is the proposed PFD. The mixer is firstly needed to mix up both feed before being fed into reforming reactor to produce syngas. Then the syngas is then cooled down before being pressured up by a compressor, before being led into methanol reactor to produce methanol. The stream is then cooled down to methanol saturation point before entering the syngas recovery unit for cost-effective purpose. The three-way valve is used to split up the streams into two, which are to be purged out and to be recovered. After the liquid stream is pressurized by a pump, the feed is then purified to meet the product specification of 95% of methanol. Then I will next pass the presentation of chapter 3 to my teammate Deborah.
Hi Deborah, and now I will talk about the chapter 3, which is on chemical engineering thermodynamics 2. Well, we are asked to generate the vapor liquid equilibrium graph of D103 mixtures, which is the mixture of methanol water, and we use the HYSYS simulation software to generate the diagrams. First, we generate the PSY diagram, second, the YS diagram. The red line represents the dual curve, while the blue line represents the bubble curve. Besides, we analyze and compare the generated diagrams with the available experimental data as well. We take the experimental data for methanol water binary systems from DBBST at temperature of 49.76 degrees Celsius. This is the nearest temperature that we managed to find. This is the generated one from the HYSYS, while here is the one we take from the DBST. From the graph, we can see that the both curves follow the same trend, despite the deviation of temperature. Besides, they follow the loss law too. However, we can see that the DBST one is not as smooth as the HYSYS, maybe due to the experimental error, for example, the non-constant temperature. Also, we find out that the vapor pressure of methanol is around 90.3 kPa for the HYSYS simulations one, while for the DBST, the vapor pressure of methanol is around 52 kPa. And here is the graph for the YS diagram, generated one and the DBST one. The comparisons is almost the same as the previous one, as the both curve has the same trend and follows the loss law. Also, the DBST one is not as smooth as HYSYS due to the experimental error, for example, the non-constant pressure. Apart from that, we also construct the phase envelope of D103 mixtures, and we use the HYSYS simulation software as well. Here is the bubble point data, and here is the dew point data. From these two sets of data, we can generate the PT diagram. The red line represents the bubble curve while the blue line represent the dew point curve. But in this one we can't see that obvious because the points are almost the same. Next, we do the price calculations. For the reference we found online, we have found that the range of operating pressures for steam decay reforming is between 3 to 25 bar, which is equivalent to 300 to 2500 kPa, and for the temperature is around 700 to 1000 degrees Celsius. So we just assume the pressure to be 1400 kPa and temperature at 815 degrees Celsius. In solving the equation, there are some requirements and methods. We need to make sure that the process is designed to be separated into two streams, which is the vapor and the liquid. Also, we need to ensure that 95% of excess water is removed. So we use the high-C simulation software to design for the process. First, we just insert the composition for each component in stream 3, and the condition, for example, the temperature, pressure, and the basic formula for it at 100 kg mole per hour. Then we add a condenser so that the stream 3 can be cooled down. The acid stream from the condenser is measured to be in liquid vapor phase, so that we fulfill the requirement of the question. And last, the resulting stream is able to separate into two streams, which is S4 the liquid phase and S5 the vapor phase. Here are the details of the simulation process. First, the flow sheet diagram, we can see that there's a stream 3 here, and with a condenser, this is the energy stream, and the stream exiting the condenser is separated into two streams, stream 5 and stream 4. Here's the condition in S3. Then the composition in stream 3, the condenser, and the temperature drop in the condenser, the delta T. Here's the conditions for the existing stream from condenser. And for this part, we can find the mole fractions of vapor over liquid by just dividing the vapor phase fractions with the aqueous phase fractions. The vapor phase fraction is found to be 0.8909, while aqueous phase fraction is 0.1091. And we can get that the mole fraction of vapor over liquid is at 0.1659. Here is the mass flow in condenser out, and now we can check whether 95% of excess water is condensed or not. For this part, we need to divide the mass flow of H2O in aqueous phase with the total mass flow of water. And from the high-C, we can see that the aqueous phase of water is 196.4879, while the total mass flow is 206.8154. And by dividing, we can get that 95% of water is condensed, and thus it will be removed through the liquid outlet S4 in the separator method. Here is the conditions in separator. Here is the compositions in separator. And finally, we get the results. We managed to separate S3 into two streams, S4 and S5. And the mole fraction of vapor over liquid is at 0.1659. The vapor compositions and the liquid compositions of the resulting streams S4 and S5 are shown in this table. The vapor compositions is from the S5, while the liquid compositions is from the S4. So that's for the thermodynamics part. And now I will pass to my friends Azrizan to talk about the separation part.
Hi, I am Azrizan. I am going to explain about chapter 4 of this project, which will be the separation process 1 part. So the objective of this chapter is to design a distillation column for a methanol purification unit, and also we need to determine how many number of theoretical stages needed in that distillation column, which the distillation column need to be operated in optimum reflux ratio. And also, in order for us to get the number of theoretical stages needed, we need to draw a graph by using the Metcalfe-Thiele method. So first thing first, we need to know the composition at the feed, the distillate, and also at the bottom. So by using this formula over here, we will have all the composition at all streams. And since we are more focusing on the methanol production, and this column over here will give us the XF, XB, and also the XD, which will be needed later if we want to plot the graph. And after that, the first thing we need in the graph is the 45-degree line and also the equilibrium curve. So after we plot the 45-degree line, we might need some data for the equilibrium curve, and by using this formula over here, we will have all this data after all the calculation done. And this data over here is the data we need to plot for the equilibrium curve. After that, we need to plot the composition of XF, XB, XD that we got from the earlier calculation at the 45-degree line. And after that, we need to determine and draw the Q line by using this formula, Q equals to 1 minus F. F is actually the percentage of vaporized distillate, which is 95%, which will make it 0.95, and also will make Q is equal to 0.05. So after we plug in the value of Q in this formula over here, we will have all these points that we need to plot for the Q line. And after we draw the Q line, there will be an intersection point between the Q line and also the equilibrium curve. And that intersection point is what we call as the minimum reflux ratio, which is at 0.1018. And after the Q line and also the determination of the R min, we need to draw the rectifying section operating line in the range of 1.2 R min to 1.5 R min. R min is the one that we got from earlier calculation. And in this project, we use two trials, which is 1.2 R min and also 1.5 R min. And after we draw the enriching line, we will have to draw a stripping line to connect from the XW point to the intersection of enriching line, also the Q line. And after that, we will need to draw some stages to determine how many number of stages are needed. So after all the lines are put into places, we will have this graph over here. This trial one, we are using the R min equals to 1.2 R min, and the number of stages needed is 3.62 and also one reboiler. And if we use the second trial by using the R equals to 0.1527, the number of trays will be 2.98 trays and a reboiler. So we have decided to choose to use the R min equals to the R equals to 0.1527 in designing this distillation column of methanol purification unit. This is because we got to see that the higher the optimum reflux ratio, the lesser the number of trays needed. So when there is less number of trays needed, the cost in operating the distillation column will also reduce. So yeah, that is all from me. Thank you.